Welcome to Get EDUCARE. Today, in class number 16, I will explain what is hysteresis loss, what are the formula of hysteresis loss for different conditions. Friends, today we will learn something new about the hysteresis loss which may not be available in different textbooks and which is very helpful for your exam point of view. So, I request all of you to go through the full class attentively. This is a transformer, the primary winding, and this is secondary winding, and this is the core of the transformer. The losses in the core is called core loss or iron loss. There are two types of core loss or iron loss. One is the hysteresis loss and another is the eddy current loss. Here the core loss depends upon the supply voltage and frequency. Since the supply voltage and frequency is constant, therefore the core loss is also constant or fixed loss. At no load condition, that means no load is connected in the output terminal, when a AC voltage is applied to the transformer primary, then transformer draw a current I of mu, that is called magnetizing current, for the establishment of flux. The flux which is passing through the transformer core and links with both primary winding and the secondary winding. This is the flux phi. Since the voltage is AC, therefore the current, magnetizing current, will be also in alternating in nature, that is the I of mu, magnetizing current versus omega t. Similarly, since the magnetizing current is alternating in nature, therefore the flux which is passing through the transformer core and link both primary and secondary winding is also alternating in nature. This is the flux waveform, sinusoidal. Here phi equal to phi m sin of omega t. Now, to understand the hysteresis loss of transformer, I take a small piece of iron of transformer core. That means I take a small piece of iron of transformer core. Suppose this is the A and B. This is the transformer core A and B. Now, at point, suppose this is the X, Y, Z and P, Q. At point X, the current is 0, therefore the flux is 0. The magnetic dipoles of the AB portion of iron part is randomly oriented in different direction. This is in at point X. The current is increasing. Okay. At point Y, current becomes maximum. Therefore, at point Y also the flux is also maximum. If I draw the magnetic dipoles of AB section of iron part, here at point Y, the magnetic dipoles are oriented in a systematic way, in this, suppose in this direction. Now from Y to Z, the current is decreasing, and at point Z again the current becomes 0. Therefore, again this is the AB portion of magnetic AB portion of magnetic core material, this is in at point Z. Point Z. Again the magnetic dipoles are randomly oriented. At point P, the magnetic flux is again maximum, but in reverse direction. Since the current is in reverse direction, here the flux is maximum, again maximum, but in opposite direction of y. Therefore at point, this is a AB portion, the magnetic dipoles this is the at point P. The magnetic dipoles are again arranged in systematic way, but this is in forward direction, this is in reverse direction, opposite direction of y, forward direction, reverse direction. That means for every half cycle, the magnetic material is subjected to change of orientation of dipole. Due to this orientation change in every half cycle, there is losses in the transformer core, here in the transformer body. This is called hysteresis loss. That means we can say hysteresis loss is the power taken by transformer core due to change of orientation of magnetic dipole for every half cycle, by in every half cycle, due to time varying current and time varying flux. If I draw the hysteresis loop, that means BH curve, here in y coordinate, this is the B flux density, that is equal to flux by area, and in x coordinate, this is the H magnetic field intensity, that is equal to MMA by length, that is equal to Ni into L, AT per meter. This is also I can write down magnetizing current I mu. Okay. When the current is 0, then flux is 0. Current increasing, flux is also increasing in the magnetic material. At some point, current is increasing, but the flux is not increasing. That means magnetic material gets saturated. Here, that is the saturation point. Now, if I decrease the current in this direction, then flux will decrease, but it will not decrease in the same fashion of increasing. When the current, again current is 0, here current is 0, but flux is not 0, this amount of magnetic flux is called residual flux. If this is the O, this is the X, O is the residual flux. If I again further decrease the current in the reverse direction, current direction is reverse now. Now here at point flux becomes 0. This, suppose this is the Y, this point OY is called the coercive force, negative coercive force. Again if I decrease the current in the negative direction further, then flux will increase in the negative direction in this way. Again the magnetic material becomes saturated here. Now again if I increase the current, the flux is increasing, flux also increasing, and it will like this xyz. Suppose this is P. Here OX is the positive residual flux. OY, here positive residual flux, OY is the negative coercive force. OZ is the negative residual flux. And OP is the positive coercive force. This is hysteresis, loss per cycle is given by area under one hysteresis loop. This is the area under one hysteresis loop. Therefore, the total hysteresis loss is given by total hysteresis loss W of H is given by area under one loop into the supply frequency F, that is given by WH equal to some constant B max er power x V into F, where eta is called Stizman's constant. Or hysteresis coefficient. Hysteresis coefficient. X is called Stizman's exponent. And its value varies from 1.5 to 2. For silicon steel, the value of X is 1.6, and V is not the supply voltage. Be careful, it is not the supply voltage, it is the volume of the core. And F is the supply frequency. Therefore, we can write down the hysteresis loss W of H is equal to hysteresis coefficient in Bm, maximum flux density, er power 1.6 into volume of core into frequency for silicon steel. This is the hysteresis loss for silicon steel. all of you know the EMF equation of transformer. The EMF equation is given by E equal to 4.44 phi m F into N, where E equal to induced EMF, phi equal to maximum flux, F is the frequency, N is the number of turns. Now phi m is the Bm into area, flux density into area, and E proportional to V, supply voltage. Therefore, I can write down V equal to 4.44 Bm A into frequency into number of turns. Therefore, if F is come that side, V by F equal to 4.44 Bm A into N. Once the transformer is constructed, the area is fixed, the number of turns is fixed. This is fixed, these two quantities is constant. This is also constant. Therefore, I can say V by F is proportional to Bm. Always remember this relation. It is not only applicable for transformer, it is also applicable for induction machine, it is also applicable for alternator also. Supply voltage by frequency is proportional to maximum flux density. Just few minutes back, we have derived two relation. One is hysteresis loss W of H equal to some constant into Bm power 1.6 into volume of core into frequency. Again, we have derived the supply voltage by frequency is proportional to B of M. Let us take some conditions. Suppose case A, where V by F equal to constant. When V by F equal to constant, then from this relation I can say V by F proportional to Bm. Since V by F equal to constant, then Bm will also be constant. From this relation, WH equal to eta Bm power 1.6 volume and frequency. In this term, it is constant. Bmax, since V by F is equal to constant, therefore Bmax is also constant. The volume of the core is also constant. These three terms is constant. Then we can conclude that W of H is proportional to supply frequency. This is one of the most important relation. We have to remember always this W of H is proportional to frequency when V by F equal to constant. Therefore, I can write down W of H equal to some constant K1 into of F, where K1 is the constant. Now, case B. When V by F is not the constant, it is the variable. When V by F is variable, then voltage by frequency proportional to Bm, it is variable, it is also variable. Now, W of H, hysteresis loss equal to the some constant eta Bm এর power 1.6 the volume of core into frequency. The W of H equal to, this is constant, in place of Bm I can write down V by F, since B of M is some constant K into V by F. Therefore I can write down, in place of Bm I can write down V by F in power 1.6 into volume of core into frequency. Actually it is the proportional to, since this is constant and volume of the core is constant, therefore I can write down W of H is proportional to V power 1.6 into F power, this is 1 minus of 1.6. That is W of H is proportional to V power 1.6 and F power minus of 0.6. This is again one of the important relation. Have to remember, this is applicable when V by F equal to variable, not constant. Therefore, we can write down the hysteresis loss W of H equal to some constant K3 into supply voltage power 1.6 into supply frequency F power minus of 0.6. Let us practice a numerical. For a single phase 2 winding transformer, the supply frequency and voltage both increased by 10%. The percentage change in hysteresis loss is how much? Both frequency and voltage increased. Okay. In order to solve the numerical related hysteresis and eddy current loss, you have to first find out whether V by F is constant or variable. Here frequency is increased by 10%. As well, voltage is increased by 10%. Therefore, V by F equal to constant. Voltage is increased by 10%, frequency is increased by 10%. Therefore, V by F equal to constant, ratio maintain. For V by F equal to constant, all of we know the hysteresis loss W of H equal to some constant K1 into F. Now, let frequency equal to 100 Hz. After 10% increase, F dash becomes 110 Hz. And voltage equal to 100 volt. Then after increasing 10%, it becomes 110 volt. Therefore, from equation number 1, W of H divided by W dash into H equal to F divided by F dash. Therefore, I can write down W of H dash by W of H equal to F dash by of F, that is W of H dash by of W of H equal to F dash equal to 110 and F equal to 100. From both sides, F dash by W of H minus of 1 equal to 110 by 100 minus of 1. Therefore, W of H dash by W of H divided by W of H, it becomes, if I do the simplification, 10 by 100. Therefore, percentage of change in W of H dash by W of H hysteresis loss equal to 10 by 100 into 100%, that is equal to 10% plus of 10% increase. Therefore, the change in hysteresis loss is plus of 10% is the answer. Practice another numerical IAS 1994. A transformer is designed for operating on 60 Hz. Supply is worked on 50 Hz. Supply without change its voltage and current rating. Then its hysteresis loss is increase, decrease, no change or cannot determine. Initially, the frequency f was 60 Hz. Now the frequency f dash becomes 50 Hz. That means frequency is decreased. Initially, the voltage is no change. That means voltage no change. Now we have to find out whether V by F is constant or variable. Now V by F, here V equal to no change and F decrease. Therefore here V by F equal to variable. Voltage change nahi, change has no change in voltage, but that is change in frequency. Therefore V by F is variable. If V by F is variable, then all of you know the hysteresis loss formula will be W of H equal to some constant K3 into voltage in power 1.6 into frequency in power minus of 0.6. Here voltage is constant, no change in voltage. Therefore W of H is proportional to F in power minus of 0.6. Here, since the hysteresis loss is proportional to F in power minus 0.6, therefore if the frequency is decreased, then hysteresis loss will increase, since it is the minus inversely proportional. That means here W of H is inversely proportional to 1 by F in power 0.6. If frequency is decrease, the hysteresis loss will increase. Answer, this will increase the hysteresis loss. Option A is the correct option.